All right, so today we're going to move into chapter 5, which is applications of integration. Um, we're just going to do two sections. There's more there, but I think the time can be better spent. And then Wednesday, we're going to move into chapter 6. So I should add that the university observes July 4th on Monday, so we won't have anything Monday. So we'll reconvene on Wednesday. But we're going to kind of work backwards here. First, we're going to do section 5.5, which is finding the average value, excuse me, of a function, and specifically a continuous function, meaning that it's friendly on a closed interval. In other words, some graphical context. Say that, a good example, this is temperature over the course of a day. This is the time. You might start out wherever and it might get warm and then cool off, something like this. So this will be my 24-hour mark. This will be my 0 mark. I'm going to call that A and B. And the idea is what is the average over this interval? And if I'm just going to eyeball it, it's probably somewhere in here. What is that value? We're going to find it precisely. So the reason this is an issue for integration is because there's essentially infinitely many values here. So how do you find the average of that? So a little context. If you think about average of a finite group, say the ages of the students in this course, if each age is X, typically we refer to average with a bar, X bar. This would be the average. So for finite values, which this is not, you guys know how to do this. You add them up. You add up say the ages. Say we'll have n of them, and maybe in this course we have 20. You add them up and you divide by how many. All right, everybody knows how to do that. So that kind of bridges into this problem. Okay, so I'm going to do a little derivation. We're going to end up with a nice formula. So a little bit more specifically, I'm going to say for a continuous function, I'm going to call it f, and we're going to be interested in a specific interval, right, a closed interval a to b. What I'll do to start out, I'm going to choose n, whatever I want n to be. You can make it 5, you can make it 5,000, equally spaced. Sample points on the x-axis. All right, so I'm going to call those x1, x2, etc., up to xn, however many you want. So if I think about an x-axis, I'm going to choose these points. I'm not going to do a drawing here. You can envision this. But of course, each x value will yield a y value, or an f of x value. So I'm going to call those f of x1, f of x2, run out of room, sorry, f of xn. Okay, so we have x values yielding function values. So, if I have a continuous function, maybe I choose, 5,000 data points. And that would give me, I'm going to use again the bar, so this will be my average of the function. That'll give me a nice approximation. Of course, the more I have, the better the approximation. And again, we go back to this same philosophy, add them up, add up all those function values, divide by how many, you have a nice approximation. The thing about calculus is, though, we're typically not interested in approximation, right? We're interested in exact. And you can just picture it. You know, if I go back to this, let's use this. You know, I choose some values, so these are the function values, and I'm going to average those out like this. All right, it's okay. Well, then I do 5,000 points, probably better, right? 5 million points, better. But it's not precise, it's not exact. So this is going to look a little strange for reasons that you'll see shortly. I'm going to multiply by a very specific form of 1, b minus a. That's the length of that interval, right? That's the length of that interval. And I'm going to manipulate this a little bit. I'm just going to rearrange stuff. This isn't anything fancy. What I'm going to do is I'm going to bring this denominator, right? This is equal to this now, out front, 1 over b minus a. And I'm going to write this, I'm going to put this n under this, and I'm going to write this as a summation. So don't get too hung up on the notation here. This is a summation of all of the function values that I have, and there's my other b minus a, and there's my n. Okay, so this is just made to look pretty. So what do we do in calculus, right? I just said if we have 5, probably a crude approximation. If I have 5,000, probably better. 5 million, probably very good. What do we always do in calculus? Well, we kind of have this philosophy, well, if I have infinitely many, if I could add up infinitely many values and divide by infinity, that doesn't even make sense, I'd be good to go. So how do we, what's our workaround? Our continuous workaround is in calculus is to take a limit. I'm going to take the limit as n goes to infinity. And if I do that, f bar is now not approximated, f bar is exact. So I'm going to rewrite this as an exact value, f of x bar equals this same expression, sorry, that's an a, but I have now the limit as n goes to infinity of this summation. So this looks like a complete mess, which it really is, but you may recognize, maybe not, maybe recognize this expression from Calc 1. This is the exact original definition of the definite integral over AB. So that gives us this formula for the average value of a continuous function on AB. This is the punchline, effectively, given, all right, this is my mean notation, the bar. That's another A. That's my formula. So this is the punchline. That's what you need to know. And if you look at this thing, if you think about the finite case where you add them up and divide by how many, this, the integral is the add them up, right? That's adding up sort of all the values in very vague terms. This is dividing by the length of the interval. That's kind of like the dividing by n piece. Okay, so this is average value. And these are very abstract problems that you'll be doing. It's just find the average value of a function over some interval. There's no context, there's no word problems. They're very straightforward, they're very mechanical. I guess in reality it's just a way to have you practice some integration. Okay, so I'm going to do a few examples using this. It's not really that sophisticated. If you got through Wednesday, okay, this is the same problem. You're just going to divide by some number at the end, and everyone can do that. So let me just walk you through a couple. You see what they look like. There's just a small handful of homework problems from this section. This is section 5.5, by the way, and I'll let you go do those, and then we'll focus on 5.1, which is area, which is a much more robust section. Okay, this is kind of a warm-up. Right? This is what you call a softball when you see it on an exam. All right, so let me pause it for a second. I need to wet my whistle. Okay, so here's one example, and I'm going to write this out as you would read it on an exam or out of the homework. Find the average value of this function, x squared plus 1. So you should recognize this as your standard parabola, which is just shifted up 1 unit. And the interval of interest will be, let's say 0 to 2. So just to give it a little bit of context, let's see what this looks like. Okay. You know, this is 0. We'll call this 2. So the parabola, that's my y-intercept. The f value at 2 will be 2 squared plus 1, so that's at 5. Put that here. So on this interval, this function looks like this. So if I just wanted to eyeball this thing, where's the average in here? Probably somewhere 2.5, I'm going to guess. Right? When you do problems, especially when you're in engineering, you get an answer, you want to give it a sanity check. Right? If I get 60, I did something wrong. Right? So we're just going to use this formula. Okay? So this is the function. I'm going to say that f of x bar is 1 over, what's b minus a? That's 2 minus 0. And this is now an integration problem. So I have x squared plus 1. Okay. No big deal. Go back to what we did Wednesday. I got a half. X cubed over 3 plus x, 0 to 2. When you see zeros in a definite integral, you put a smile on your face, right? Zeros and ones are your friend. So I'm going to pop the 2 in here. 2 cubed is 8. I got 8 thirds plus 2, which is 6 thirds. And of course, substituting this in is 0. I'll just put it there as a reminder. So if I want to go back and look at my work, I know I did it. So this is what? 14 thirds over 2, 7 thirds. 2 1/3. Okay? So it's, my estimate is solid. Okay? So they all run the same, right? They're all worded the same. You know, it's maybe a little bit of a boring problem, but as I said, if you see this on a test, you know, this is a home run for you. Let's make one up here. Let's do one more. I won't write out the problem statement. It's the same. Let's go with, you got to be careful making up problems sometimes. They can get a little crazy. Let's say cosine. There's a lot of trig in this course, so don't shy away from it. I'll mention things that you need to know as we go through it. Let's pick an interval here. So let's think about what the cosine function looks like. Right? This is 1, so that's my y-intercept. And we'll call this pi, which means this is pi over 2. Right? And we'll stop there. So maybe we'll, let's say 0 to pi over 2. Which means my average is somewhere in here, right? So likely this result will have a pi in it. But clearly this is less than 1, you know, maybe a third. I don't know. We'll find out. All right, again, the average value, 1 over pi over 2 minus 0. Okay, so that'll end up as 2 over pi, so you can see where that's headed. Okay, so this will be 2 over pi. And my antiderivative here is sine. 0, 0. Pi over 2. So this will be 2 over pi, which is about, that's more like 2 thirds. Sine of pi over 2 minus sine 0. Right, so this is 1. This is 0, so my average is 2 over pi. That's more like 2/3. But I'll buy that. Okay. So again, not a very sophisticated problem. It's really just a glorified way to get you to practice integration. Okay, so what I'd like to do next in part 2 is move into area. A little bit more involved because it pulls multiple concepts, not just from calculus, but from algebra, graphing, things like that. So this is a quick section. Hit those homework problems and let's move on.